Okay. Good afternoon, everyone. Welcome to the webinar. The webinar is organized by the CFM Center for Future Materials at the USQ. My name is Wang. I will chair the webinar. So I'm going to do some bit of introduction first, and then so the introduction will be about the center and about this webinar series. And then I see the composite, the plastic composite area. It's the trend happening, and then which means the activities we are doing in the center, and then also related to these topics in the webinar. And then I'm going to introduce our speakers. So some of you know the center, and then some probably don't know. Center for Future Materials is one of the 9 centers at the University of Southern Queensland. From the name, you can say the future materials. So we certainly look at the structural material and also functional materials. Are particularly looking in charge of the functional materials themes. The center has one of the focus is on the composite, and that's including the composite development, manufacturing, and applications. So we have a lot of activities on the composite area. And then the webinar, we already have several webinars previously. We have the webinars on protrusion material, composite in the civil applications, and then this one is the plastic and the composite, and then we have some particularly focus on the Fibre recycling and robotics manufacturing. So I'm going to talk about why we selected these topics. This year actually mark as the 50 years of the composite, particularly the carbon fiber composite in the application. We know carbon fiber composite has played very important role in the aerospace. And then in the last couple of years, we see a trend, a very clear trend, is the material is going to extend from the aerospace to the non-aerospace industries. And then those including in the automotive, wind turbine, blade, the pressure vessels, and also in the civil construction engineering areas. And then the material will, from like in the aerospace, will be the small quantity, high-end applications. And then with this trend changes, it's going to be large volume, and probably the huge volume, and then with the low cost. And then there's some reasons behind for this change. Certainly, like one is the cost of carbon fibers has been significantly reduced in the last decades, and also the production is also increased significantly. Then it means the carbon fiber composite is not going to just for these high-end applications. It also can be afforded for those civil applications. And the change also means there's a lot of new considerations or implications. And then this including the fire, because in the aerospace, in the automotive space, the composite material now is going to replace many of traditional metal materials. And then the fire, it's not the problem for the metals, and then certainly it can be the problem with the composite and the plastics. So that is the reason we choose the fire. And then more and more start to look at the material sustainability. So recycling is also going to be a big issue. And then with the large volume of the application, the plastic and the composite, and then the recycling is going to be central topics. And then also with the large manufacturing, large volumes, it has the implication to the manufacturing. So previously we can use we can use the applications particularly for the aerospace, and then now we have developed the other. You need to be the high speed, large volume the production method, and then that's also including this filament winding process we're going to talk about today. The center also doing the journals. There's in the composite area, you might know, like composite part B is the top journals in all the composite areas. So I'm going to also introduce about these journals. So so these are the topics for selecting this webinar. And then I might now move to introduce you the first speaker. So Pingan, Pingan Shong is the associate professor at the Center for Future Materials. And then he is particularly on the plastics, polymers, and then one of his research area is the flame retardant. So today he's going to talk about the fire retardants for polymetric materials. Now I hand over to you, Pingan.
Okay, thanks, thank you very much for Professor Wang's introduction. Today, let me share my screen first. Okay.
Before Pingan doing that, I just mentioned that in the screen there's a question Q&A area. So everyone, if you have the questions, you can put your questions in Q&A area, and then also you can otherwise you can directly ask the speakers, and then sometimes I will pick up those questions. Yeah, continue, Pingan.
Okay. Yes. Can you see my screen?
Yeah.
Okay. Hello everyone. My name is Pingan. As just Professor Wang just introduced, I'm from CFM, University of Southern Queensland. Today my presentation is about flame retardants for polymeric materials. So before I get started, I would like to just brief my research in last 15 years. So since 2006, when I pursued my PhD degree in China in Zhejiang University. So my research is based involved in the polymer mechanical properties, mechanical properties, and the fire retardancy or polymers, basically that. So since 2006, I have published over 120 relevant articles in this, and also I developed over 30 kinds of fire retardants for different polymers, and also file over 16 patents for the basically China. And also I have successfully commercialized my 2 products basically from retardant polymers. So for today's my presentation, I would like to introduce it from the following 4 aspects. So background, the polymer materials, and 5 risks of polymer materials, and about why we do flame retardant materials. And the second part is the 5 retardants for polymeric materials and 5 retardants, and also I will introduce some budget scale evaluation methods for fire retardancy, and also I give some case studies, and following that I will give some conclusions and the key challenges we are facing now, and also give some future perspective or research opportunities in the future. So first, when it comes to polymer materials or polymeric materials, I guess some of you might not familiar with the polymer. So by definition, the polymer is a naturally occurring or synthetic molecule composed of many repeating units or monomers that are generally chemically bonded and generally with a molecular weight over greater than 10,000. So such as the common plastics, the polypropylene, polyethylene, polystyrene, or even the naturally occurring DNA cellulose or natural rubber. Also all polymers. So polymers are basically used in every aspect in modern life. So according to their structure, so polymer can be linear or branched polymer. So for linear or branched, generally they can classify the thermoplastics, so like a PP, PS, and PPE, PE. And for cross-linked polymers, we also have cross-linked polymers. The cross-linked polymers, so basically they belong to the thermal sets. For example, the polyresin on polyester. That's something. So according to the polymers' physical properties or their practical applications, so polymers can be classified in 5 major classes. So the plastics, fibers, and also the rubbers, adhesives, and coating. So as we all know, polymers. If you look at the plastic products around you, you will find that most of polymers are feature high, lightweight, high specific strength, and flow resistant or chemical resistant as compared to traditional metals or ceramic or glass. So because of these advantages, so polymers have been ubiquitously used in like many industry areas. So for example, electronic or electrical space, bio construction, all of these areas. So it reported by 2050, the global polymer production will increase to 1,200 million tons. That's a lot. So despite the many advantages of polymers and its wide application, but the problem with the polymers is their fire risks. For example, their flammability. So I just give you a very simple indicator for flammability of polymers. Here is a LOI. There refers limiting oxygen index. What is it? It's limiting. It removes measure the minimum oxygen concentration to maintain the burning of a polymer or material, any material. As we know, the oxygen in air, the volume, its concentration is 21% by volume. So if the LI of a material is smaller than 21, so it can be regarded as flammable materials. So if the Li follows between 21 and 26, it can be regarded as combustible materials. So if the Li is greater than 29, we can say it a self-extinguishing material or non-combustible materials. So if you look at the two tables, the natural polymer, the natural rubber, cotton, silk, wood, even wood, the 25, and also the very common, some plastics, some sets, all of these are flammable. Because their Li value are smaller than 26. So that means they're highly flammable. Because of this, the ubiquitous use of polymer materials has triggered a lot of fires. You can see this because it's a socket, it's plastic-based socket. It's basically ABS. And also this is the Tesla electrical car because of the short circuit, the cables and the wires in the car that cause the fire, and also the airplane, the winds, and also the flammable polymer-based fabrics, the furniture, burning fire, and also the ground fire tower fire because the use of flammable, the small unit insulating materials for the EPS, and also the even Notre Dame Cathedral because of the flammable wood structure, and also Melbourne to large apartment fire, the La Crosse apartment, and our new 200 fire in 2019. So it reported in Australia. So each year, about 100 people are killed and over 3,000 people are injured because of fire. This can cause a direct economic loss of over $1 billion Australian dollars. It's accounting for 1.2 Australian GDP. So that's just directly or indirectly due to the use of flammable material polymers. So this table just shows some very catastrophic fire incidents associated with building, high-rise buildings. So because the fire risk of the fire polymers, how to stop and how to mitigate the fire risk of polymers? So generally, we have two strategies. One is fire prevention, it's active fire protection. And another strategy is fire safety. It's about the polymer itself, as a passive fire protection. So for active fire protection, we know the fire prevention is just the fire alarm system or sensors. If you look at your ceiling, you can see every room you have smoke alarm or infrared alarm or PPE. PPE just you can, such as the fire blanket for your use when a fire happens. So for fire safety, basically it's polymer, so we can make fire retardant polymers. So that can stop. Actually, in reality, the reality is the fire prevention is just it's active fire technique, but it's not enough to stop the fire associated with the polymers. So we need to create the fire retardant polymer materials. So if you want to create a fire retardant material, you need a fire retardants. So if you look at the picture, the statistics, you can see the global fire retardant market is expected to reach $9.3 billion by 2027, and nearly half of the flame retardants are consumed by polyolefins and epoxy because they are widely used in modern life. So this map I just show you the roadmap for fire retardants. So if you look at this, as early as 3000 BC China, and also 1600 years later in Roma, the ancient people had used the vinegar, aluminum or clay as a fire retardant to treat the flammable wood-based ship or boats. And as early as 19th centuries, the first fire engineer or pioneer or Joseph, he used ammonia phosphate and borax to treat the curtain. So that's the first, that can be regarded as the first generation fire retardants for polymers. So the next generation is a highly efficient halogen-based fire retardant. But now because of the environmental concerns, so now it's gradually being banned in Europe or in the world. So next generation, the flame retardant is basically intumescent flame retardant system. Is basically made up of ammonia or melamine polyphosphate APP or maybe these things. And also the next we also have the inorganic minerals or ATH or MDH. Or in the last decade we have seen the use of nanomaterials and even recently the bio-based or biomaterials as a potential flame retardants for polymers. So how to apply these fire retardants to polymers? So generally, we have three strategies. So first strategy, we can develop intrinsically fire retardant resins or polymers. So this is here, but you also can add a reactive or additive fire retardants with polymers by solution blending or melt blending. And the last one, you can apply fire retardant coating as well. So, but each strategy has its own strengths or weaknesses, and their practical applications are strongly dependent on the physical structure, characteristics of the fire retardants and the polymer matrix. So before doing that, before we make fire retardant polymers, we need to understand how polymer burn and how the fire retardant works in the fire. So in this scheme, you can see the polymer at an elevated temperature, the polymer will thermally degrade to create the small volatile combustible products as a fuels to feed the flame. So with the oxygen and heat and the fuel, the polymer, you can maintain a fire until the polymer are totally burned. But if we want to stop the fire, polymer fire, the flame retardant can have a role to play in gas phase or condensed phase. So here, you can in gas phase, you can interfere or interrupt the polymer chain reaction or polymer burning by trapping free radicals or dilute the oxygen or fuel concentration by releasing some non-combustible gases. And also you can cool the underlying polymer by releasing water or as a heat sink. Or you can also insulate the polymer by creating a char layer as a heat barrier or some barrier. You also, last one, you can also convert the polymer into a thermostable char. Because the char is non-combustible. So you can make that's how the fire retardant plays in the polymers. So before I move that, I would like to introduce some three typical bench scale fire testing for assessing the fire retardancy of flame retardant materials. So the first is the oxygen index tester. This is a structure. It's a structure of the oxygen index tester. Here is we have oxygen nitrogen gas mixed gas supply. This is some holder. We mount the sample on the sample holder, and this is glass cylinder. You ignite the sample from the top of the sample and while chewing the oxygen content until you can ignite the sample. That's at that stage, the oxygen concentration is the LI of the molecular polymer. So the second method is UL94 test. UL94 stands for Untitled Laboratories test standard burning test. So it basically has two models: the vertical burning test or horizontal burning test. So basically in industry, and we normally we prefer to use the vertical burning test. because it can simulate the early situation of fire around the same sample and technically evaluate the fire risk and ensure it doesn't trigger the spread of the fire around it. So, generally we prefer a V0 rating. That's a flame retardant, general flame retardant requirement in industry, widely in industry. So if you want to your polymers from retardant polymer be used in industry, you need to get a V0 rating. So the last bench scale fire testing is concurrent. This is more powerful. This picture just show the picture of the fire testing. Generally, you expose your sample to a conic heater, and you also use a spark igniter to example. So by doing this, we can simulate the real combustion of material in a real fire scenario by determining the ignition time, mass loss, heat release, and smoke production, and other key fire parameters. So this really powerful fire testing facility for fire retardant materials. So next, I'm going to move to the case studies. So because time limit, I just give some 3 typical polymers. So firstly, the polypropylene, because it's a typical some plastic, and the second is the epoxy resin as a very typical thermoset and as a charring polymer. The third is rigid polyurethane foam. It's widely used in the building simulation. So first I'm going to talk about the polypropylene. Polypropylene is ranked the second most widely used plastic in the world. Just because of its low density, I think the PP is the lightest polymer in plastics. Because the low density is 0.9, and low cost and high sustainability, and is many merits. This you can see this the global PP per market size was about 77.8 million tons in 2019, and it is expected to reach 173 billion US dollars by 2027. So if you look at the applications, you can see in the wider use many industry areas. These are the car parts. Yes, you can see many of the car parts are basically made of PP. For example, PP resins and PP blends, and also fiber, glass fiber reinforced PP or carbon fiber reinforced PP as other parts of cars. So for flame retardants for PP, so generally this figure I just give some very currently most efficient flame retardant system for PP. So this is in 1998, the two have reported a combination of APP here, chemical structure here is ammonia polyphosphate, and in combination with the PER is polyol and melamine as a blowing agent. The PER as a charring agent, APP as a acid agent. So by combining them together at elevated temperature, this flame retardant can produce a formed char layer. This char layer can serve as a thermal barrier to protect the underlying polymer, so that it can make this. So this figure just shows the required loading level to make a PP with reach desired UL9 for V0 rating. So initially, we 33% need to are required to make a PP to get a V0. So in last decades, the research has focused on developing the synergistic agents with for APP to make that. So in 2016, the shadow report the use of saprolite as a synergistic agent for APP. We can get a 12.5%. You can get a V0 rating, a desired rating, and although its OI is not high enough. And recently, we can use also use the polyphosphate ester and in combination with this chemical structure, we can get at 10% you can get V0 desired rating. So basically, the ABP is a dominant fire retardant for PP. So second example is epoxy resin. So the polymer resin, as most people know, the polymer resin is widely used like coatings and the electronics. You can see here the coatings like PCB, but it's LI is as the OI is only 19%, so it's highly flammable materials. So the last case, many different kinds of fermentants have been developed for epoxy resin. But the most efficient system is fermentant system is phosphorus containing fermentants. So here we have three kinds of solutions. So you can make a reactive phosphorus containing epoxy resin, and also you can make the phosphorus containing curing agents for epoxy resin, and also you can make the additive phosphorus containing fire retardants, and you just need a very low phosphorus content. For example, this is 0.24, you can get a V0 and a high AOI, and also. So basically, the phosphorus and nitrogen synergy and also phosphorus containing fermentants are best choice for epoxy resin. And lastly, I want to talk about, but most important, recently the research has used the biomass mass as a starting module to synthesize intrinsically fire retardant EP. As a good, the fire retardant results are really impressive. So the last case study is rigid PU foam. As you know, the PU foam is widely used as a building thermal insulation because of its low cost and low thermal conductivity. So you can see this in 2022. So the global building simulation, the value can increase to over 29 billion US dollars. But it's highly flammable. You can see it's very easy to ignite. So that's why we need to make filament retardant PU foam as building materials. So I think for its filament retardant rigid PU foam, this picture just shows the roadmap for filament retardant PU foam. Sorry. And basically you can look at the top, just the additive filament retardants and also filament retardant coating. But the active fire retardants are dominant solutions. So for reactive fire retardants for PU foam, so they are basically phosphorus containing diols or polyols. So that have this reactive fire retardants only have a slightly impact on foaming process and bulk materials. It's very ideal fermentants for PU foam. But its weakness just requires a relatively high required loading level to reach a desired V0 rating. But for additive fire retardants, so basically you look at this. If you get a V0 rating, you just need a relatively lower content, by about 10%. But you can get a high LI value. But basically, at the moment the expandable graphite as a highly efficient fermentant for PU foam. But the problem with it is it can have a negative impact on the thermal insulation, and because you can see increased thermal conductivity, also increase the density. So that can also affect the foaming process and the thermal insulation as well. So the last strategy for PU foam is filament coating. It's the coating, but not many people are working on filament coating because it requires a high interface heating. But this is a copolymer where we have recently developed. So we can show you these results. The left is the untreated PU foam. The right is the filament retardant coating PU foam. So you can see the untreated burn very fast, and this is self-extinguish or even you cannot ignite. So you can see its LI is very high. It's 35.5 out of V0 rating. So next, I'm going to share our recent work on filament unsaturated polyester foam. This is just a microfoam in the laboratory. You can see this. You can distinguish in 1 second. If you ignite and the fire is very small, you can see that I can. On top of that, its strength very high. Its compression strength it's about 10 megapascal. It's much stronger than the rigid PU foam and EPU foam. Although its density is higher, but we are doing its evaluating its semiconductivity.
You have 4 minutes.
Okay, I will finish. So lastly, I'm going to some conclusion. So if it's clear, it's very important to develop 5 tandem polymer materials in view of 7 lives of properties. So for non-tandem polyolefin, you need to design the phosphorus or nitrogen containing filtrants in combination with a synergistic agent. For Charon Composites, for some EP, you'd better use the reactive or additive phosphorus containing from retardants. Also, you can develop bio-based intrinsically purified retardant resins. For PU, you'd basically use the reactive fire retardants. And also, you can use the EG as a fire retardant, but you need to use need to combine with the first containing filtrants. Also, you can create a fire retardant coating. So, but since even if we have made greater advances here, but we need some challenges we still have. So, for example, the non-renewable raw materials for filtrants also use a lot of organic solvents, also some molecular design for leading to the low efficiency or the mismatch between the filtrants and the polymers, and the negative impact on the polymer materials properties of mechanical electrical processing. So in the future, we need to do much more work on using the renewable substance and raw materials, and your green chemistry. Also, you can develop intrinsically fired retardants, or you should to select the right from the fired retardant elements or groups for mechanical for particular polymer matrix. You can design the eco-friendly phosphorus or nitrogen kind of filtrants, and also you can use use of synergistic effect. So that's my presentation. Thank you for your attention.
Thank you, Pingan. Any questions from our audience? So certainly, like as I mentioned, the polymer and the polymer-based composite, we are going to use to replace lots of metal materials used to be the metal, using the metal, so replace that. And then fire safety is going to be an issue, and then how the strategies we can prevent the fire, and then make the material as fire resistant as a metal. So that is mainly Pingan's topic. I saw there's one audience put the question in the Q&A, and he is talking about the geopolymer can be one way because it's the ceramic based material and it has the good fire resistance. The actually geopolymer is not polymer. So geopolymer is the ceramic concrete based material. So that is very different. The type of materials.
So can I answer 2 questions from QA?
Yeah.
So for the first question, so it's from Pyramid. So it's good question. So the graphene, I have doing some much work on graphene as a fire retardant for polymers. So the graphene itself is a non-combustible carbon materials. It can be only used as a synergistic agent. It cannot be used filament retardant alone because it does not contain any filament retardant elements. So if you want to if you want to use graphene as a fire retardant, you need to use it in combination with the other traditional phosphorus or nitrogen containing fire retardants. Because it is this loading level, because it's the cost and it's the color. I strongly encourage you can add only less than 1% into polymers. Otherwise, you can increase the electrical insulation property of polymers or superconductivity. So, and the second question, so for team building materials, I think it's good because it depends on the solubility of the filament retardants. If for team treatment, we have basically two strategies. One is you can use the filament retardant coating for the building materials. The second is you can use the water soluble the filament retardants. For example, the ammonia phosphate or poly soluble ammonia polyphosphate as a fiber retardant to treat the timber. And you dry, then you can use it. You can make a fire retardant timber.
Okay, thank you, Pingan, and thank you the questions from the audience. Just conscious of time, and then if you have further questions, you can send the emails to Pingan directly, and then he will be happy to answer those questions.
Yes,
the second presentation will be given by Salwan. Salwan is our industry collaborator. He is from an organization is called Pingan. So that is another to showing the activities at the CFM. Yes, we working with the industry closely. And then his topic is about the circular economy for the plastics industry. So that is also very important issues. And then the plastics, they are so good. That's the reason it has been replaced a lot of metals, ceramic, glass, these materials. And then they have been used so widely. And then the issue with the pollution is really how we actually to use the material more wisely, and that is currently is a big issue. So I hand over to Salwan, please.
Thank you, Hao, for this introduction. So as Hao said, my name is Salwan Al-Assafi. I'm the General Manager for R&D for Paintback. A little bit of background on myself. I'm a material scientist, so I've been in the R&D field probably for the past, I would say, 20-25 years. Did a lot of work on composite materials, polymers, plastics, even some work on construction materials. I worked in New Zealand, Australia, the US, and Dubai. So I've been here in Australia for the past 4 years. Previous to that, I worked in New Zealand. So just to give a little bit of background on Paintback. Probably some of you is not aware of what sort of activities we do, and I just have to warn you that this is going to be more about the company and the programs that we have rather than on results of programs, because most of these programs are just starting. So it's quite a young organization, and most of these programs just being kicked off are going to be kicked off in the next few months. So Paintback is a not-for-profit organization that was set up by the paint industry in Australia to manage paint waste, collect it, and then look for applications, for end-of-life applications for the waste. And that waste can be paint itself or can be packaging. So companies that set up this organization, I would say they have 90% of the share market in Australia, if not more. Companies like Dulux, PPG, Hames, and Resine. So what happens to paint? How do we deal with paint? So all the DIY and trade painters take their whatever unwanted paint, so like partial full containers, or sometimes empty containers, or maybe half full, in some cases even almost full containers, to collection sites. From these collection sites, which we have like over 160 throughout Australia, all this paint gets transported to aggregation sites, where the paint will be separated depending on the type of paint. So water-based paint will be on one side, the solvent-based paint will be on the other side. And then we go through the depackaging and then treatment. After that, the role of the R&D starts, basically. So what are we going to do with all this material? What are we going to do with all these material streams? So we get 4 material streams. We get water-based paint, which is latex-based paint, solvent-based paint, metal packaging, and plastic packaging. So, of course, our interest is really revolves around circular economy. We try to reduce our reliance on virgin materials, and this is what circular economy is all about. So you want to keep reusing the material that you have in your, whether it's for paint formulation, whether it's in the packaging, keep reusing it so that you can reduce your reliance on virgin material. In the case, for example, for plastics, you don't want to use virgin polypropylene, you want to recycle or reduce the amount of virgin polypropylene that you use. So this is our model of circular economy. The paint, after the paint is used, paint is collected. Currently, the solvent-based paint is used as coal replacement in cement kilns. So it's a waste to energy solution. The plastic will go into, I'll go through one of the programs that we're working on, which is recycling the plastic, cleaning it, shredding it, and then reusing it in pails for paint. And then after that, filling the pails with paint, and then so on and so forth. We just keep going this way. So this is what's called circular economy. We are also working on some programs that, like, as you can see, the green path. And instead of just recycling plastic, we're also working on extracting valuable chemicals in paint so that we can take it out and then put it back in the paint formulation, and thereby generating another circular economy solution. So you're probably familiar with the waste hierarchy, this pyramid. So the least preferred solution is landfill, so disposing to landfill. Our main aim is to divert as much material from landfill as possible. So our aim is to go over 90% diversion in terms of material going to landfill. One step above that is energy recovery, which is waste to energy. As I said, like, it's not, I would say, a great outcome. It's better than landfill, but we would like to go to higher solutions. So energy recovery is like using our solvent-based paint, for example, to replace coal. So it's waste to energy. And then we go to recycling, which is like what we do with plastic. We take the plastic, clean it, shred it, and extrude it, and pelletize it again, and then reuse it. So that's the recycling. Reusing is if we use the paint as paint. So that's reusing the paint. And that's not really at this stage on the cards, because there are a lot of limitations on reusing paint here in Australia. And of course, the most preferred solution is avoiding waste altogether. In terms of R&D portfolio, our current programs, there are, I would say, 3 different areas that we are working on. The main focus is on water-based paint and on plastic packaging. Water-based paint, it constitutes about 55% of the material that we collect. So we collect annually about 8,000 tons, 8 to 9,000 tons, so 8 million to 9 million kilograms of total material. Around 50-55% of that is water-based paint. So we're looking at several opportunities. It's probably beyond the scope of this presentation because the focus here is more on plastic. So we're looking for some solutions in concrete, in some of the construction materials, and also for in energy recovery. For plastic packaging, it's about 6%, so we collect around 400 tons a year. And that's polypropylene. It's mostly, I would say, over 90% is polypropylene. So we're looking into recycling it into paint pails. And we have one new program, which I'll be talking about shortly, with USQ on using plastic in plastic composites. We can also use it in energy recovery, which is core replacement. And FRP composites, as I mentioned. Solvent-based paint, that's currently we are only, definitely it's not going to landfill, it's all going to core replacement because of the high calorific value of solvent-based paints. I would like to focus a bit more on recycled plastic packaging. That's the program that we currently, it's a pilot program that we are running with our partner, Estron Sustainability. So the idea was, the driver behind this project was we wanted to know that if we can collect this, all these plastic pails, and as I said, we're talking about around 400 tons of polypropylene. Polypropylene, as Pingan mentioned, that it's a versatile material. It's a really good plastic to use. It's got good engineering properties. However, unfortunately, the percentage of polypropylene that is recycled in Australia is really low. It's talking about, I think, around 8%. Globally, is only like 1% is being recycled. So it's a very low recycling rate. So we're trying to change this. So we're working with Estron on developing a process to get the pails, get them cleaned, shredded, and then remove all the whatever contamination we can remove, and then perhaps convert it into resin, extruded into beads that can be used for all sorts of other applications. So as I mentioned, we're collecting about 400 tons. Only 20% of it goes to waste to energy, replacement for coal in cement kilns, and then the 80% currently is going to landfill. And this is something that we are aiming to change. And we are, I think, I would say, in an advanced stage in this program, probably within the next, we're expecting to launch the product, which is the output from this program in the first quarter of next year. So how does this process work? So we got like paint pails collected by paint bag. As I said, we've got over 160 nationwide collection centers. And then waste contractors, they empty all the pails and give them clean. And then these pails go to Estron Sustainability. They shred the pails and give them a good wash. After that, the shred gets further washing, and then it gets granulated. And after that, we go through an important step for this process is polymer sorting, because this is a waste industry. You do get all sorts of other materials, other polymers. You cannot really have very good control over what people put in these collection centers. So we go through a process to polymer sort the shred. So we remove all other polymers and we just keep polypropylene. We remove, normally we get a lot of PE, polyethylene, so we remove all the polyethylene, and then we end up with a fairly high percentage of polypropylene. This polypropylene, we take it, we extrude it, pelletize it, and then we end up with polypropylene beads or pellets. So in terms of how does that work? So we've got, for different states, we have different processes. The main volume is really coming from the large states like New South Wales and Victoria, and Queensland also. These three states, we get large volumes from them. In New South Wales, we have an automated system that's called HAZPAC. It's a HAZPAC, so it's for mass production. They put lots of large volume of pails, and then it'll get all these pails get shredded. So liquid paint goes one side and plastic goes to the other side. The plastic after that gets taken out of this machine, and then it goes to washing and further processing, while paint goes to somewhere else where we can deal with it, depending on what is the end application for it. As for the recycled plastic, we had, when we started this program, we had a lot of issues with contamination. As most of you probably know, when you're dealing with the waste industry, that is a major issue. So you're always aiming to get good consistency, and that is quite difficult when you're dealing with the waste industry. So you have to have some sort of, I would say, add some features to your process to improve the robustness of the process. So for instance, for this particular process, we introduced more than one sorting step to remove, for example, the color, because we want pails to be a certain color, for example, white. So we remove all the dark colors. And then we have, of course, the polymer sorting, as I said to you, which is an online feature we have on the machine itself. So it'll scan the shred and remove all the other polymers. So we end up with resin beads, recycled resin beads, and then we add it to virgin. So we don't use 100%. We've gone through a testing process. We determined that a safe percentage of recycled content would be around 30%, to be on the conservative side. So we have this 30% of recycled polypropylene. We add it to virgin material, and then we add, in some cases, could be white masterbatch to give it the white color, or it could be leave it, depending on the client, or perhaps we leave it without any color. So the process is first to get the shred granulated, wash it, get the excluded material out. So that's all the dark, for example, you can see here under the excluded material, that's all dark plastic that won't really, that is not suitable for this particular product. We have to remove it. And then we go through the color sorting, polymer sorting, and then we end up, after extrusion, we end up with the final material, which is bead. So what you can see here on the photo on the right-hand side, this is actually the blend of virgin material and recycled material. So the recycled one is the more on the bluish side. It's like bluish gray color, and the white or translucent one is the virgin material. So this is the pail that we are working on. It's a 2-year pilot project that's commenced in New South Wales. We're aiming for 30% recycled content, and we don't want to compromise in terms of performance. So we're maintaining the same performance, and we, in terms of GHG reduction, we're getting about 50. The aim is to get about 53 tons GHG reductions. We also have a program with Monash University. So that's, if you remember when I was talking about the circular economy that we're trying to work on, is recovery of high value chemicals. So on one of them, the highest value actually chemical in our paint is titanium dioxide. So we started a program just over a year ago with Monash University on extracting titanium dioxide. And this works currently only on water-based paint. So we're only working on water-based paint. So the material gets, the water-based paint gets sonicated, and there's got different, like they study more than one process, but in general it gets sonicated and then separate the polymer from titanium dioxide, and then you end up with an emulsion which you can put back in the paint. So this is another circular economy solution. So you separate titanium dioxide from the rest of the paint, you remove it, and then you put it back in a new paint formulation that can go to another customer and they can use it as paint. So that's clearly, it's an important program because this way we will reduce our reliance on virgin titanium dioxide. And at least, even if we achieve percentage, maybe 30, 50% reduction, that is still quite an achievement. The last two programs I would like to finish with is it's a new, both of them are new programs, as Hal mentioned, that we are partnering with USQ and with RMIT on the new ARC research hub for transformation of reclaimed waste resources to engineered materials. So this is a program that is just starting now. Actually, we just kicked it off, and we're working with several partners, several industrial partners, and with USQ on two separate areas. The first one is the recycled polypropylene, recycled fiber composites. So this program, the idea, we're trying to solve two waste problems. So we've got polypropylene waste as an issue, and then we have fiber waste. So fiber can be natural fiber, carbon fiber, glass fiber, any other type of fiber. So we're trying to combine the two and come up with a material that is, higher performance material. Potential applications we're looking for most likely to be in the construction industry, decking, window and door frames, and this kind of applications. And it's I think we're keeping our options open. Initially, probably most of the ones going to focus on how to combine the two materials and how to optimize performance, and then we'll be looking at different applications. The second program that we're working with HAL and USQ is geopolymer concrete, and probably all of you know that it's an emerging technology. That geopolymer concrete, which is called as green concrete, can provide significant reduction in GHG, greenhouse gases. So more than 80% reduction in greenhouse gases. So this program will be looking into using our water-based paint as in the formulation, in the geopolymer formulation. So we want to see what sort of advantages. We've done some initial work and showed that this is a very promising area, and there is good compatibility between our water-based paint and geopolymer. So we're trying to see what sort of value we can add to this material. Again, we just kicked off this program, so hopefully if we have another webinar in a year's time, probably we'll have some results that we can share it with you. That's it for now. Thank you very much. If you have any questions, I'll be more than happy to answer.
Yeah, thank you very much, Salwan. I'm waiting for the audience question, and then Salwan, I see the Q&A. There's one question here. Leo asked, have you attempted to add those paint waste to the concrete and then to produce the polymer concrete?
Yes, that is a separate program. We are working on it. We are actually partnering with SmartCrete CRC, and that is it's a new CRC. We are actually a core partner in this CRC, and that is headed by Macquarie University, Western Sydney University, and Swinburne University. And we've got quite a few partners from councils to Vic Roads, Transport for New South Wales, and quite a few authorities as well. So, and we are working with some concrete companies directly. So this is one of the probably most promising potentials for water-based paint, is to use it in concrete.
Yeah, right. Okay, any more questions? So certainly, like, we are very pleased to see the industry also has driven these the global issue, like the material, the plastics, and then how we can improve our usage and then promote the circular economy. So certainly, plastics is the materials currently behind compared to the glass and the metals. So there's a lot of activities can be done, and then it means also like if we do it properly, and then we can achieve a lot. So thank you very much, Salwan.
Thank you, Al.
And then I'm going to the next one. So next one is going to given by Venkata. As I mentioned at the beginning, like the carbon fiber composite, moving from the aerospace and then moving to those non-aerospace applications, there are going to be a huge volumes. And then carbon fiber composite, certainly there's a possibility for the recycling. We have the problem with the glass fiber composite because the glass has a low value, and then glass fiber has a low value, and the carbon fiber has a high values, and then the industry has more interesting to doing that. So I hope like once we start with the carbon fiber composite, and then once the technology getting more mature, and then the exercise or activities can further move to the glass fiber composite as well. So I hand over to Venkata.
Good afternoon, everyone, and also hi to our friends in Europe and elsewhere. It's really a pleasure today talking about carbon fiber recycling. Some of the thoughts and opinions myself and the composites community today. I'm a materials engineer, and my focus areas are in structural and non-structural composites. In USQ, I work with two major areas. One is in the area of the carbon fiber reinforced composites, where I look at the thermoplastic composites manufacturing for large volume, low cost manufacturing. And I also look at recycled carbon fiber and how to utilize them for end users, which are different from aerospace. I also work in the area of sustainable composites, specifically biocomposites from natural fibers and fillers, and also how to use different waste streams into valorizing composites and value-added materials. I work in the USQ Center for Future Materials, which has recently got very impressive upgrades, dual brader, and also a brand new $6 million building. I believe this opens up a lot more opportunity and avenues to engage with industry and researchers throughout the world. So I'll start with a simple thought here, which is when we look at the energy to produce 1 kg of pristine carbon fibers, it's quite high than what is required to recover 1 kg of recycled carbon fibers. So you look at a very vast difference between what sort of energy is required from going from the precursor all the way to the fiber architecture. So combined with that is the fact that when we decrease the energy in a specific process, new opportunities come up. And that's in fact what's happening in the wind energy sector today, where with the increase in the length of the wind blades, what you're seeing is carbon fiber being used more and more. and glass fiber fraction and how much of glass fiber is used in those wind blades is decreasing. If we look at the global view and where the carbon fiber demand comes from and how the carbon fiber applications also are producing a vast amount of waste, what you will see is aerospace, which is the traditional, I guess, the custodian of carbon fibers, if you will, since the last 5 decades, is at the foremost position that produces the most amount of demand. And then you have wind energy, which is gaining ground very rapidly. In terms of what processes do you use carbon fiber the most, that would go to the pre-pick type processes, which are used in fuselages and other aeronautical and aerospace applications. And pultrusion and filament winding is also a very significant process, which is taking up a major chunk of the global CFRP demand. If you look at the demand, it's not stopping anytime, although COVID has impacted it a little bit. You're seeing an increase in the demand in the carbon fiber reinforced plastics and composites throughout the years. However, the growing demand for carbon fibers is limited, and this limitation comes in from the cost of the carbon fiber. So we know that there are novel processes and there are novel precursors these days where you can produce carbon fiber from not just synthetic petroleum-based precursors, but also from sources such as lignin, with different viability and a different performance profile. So cost being the central point, what you would see today is what Professor Wang alluded at the start of this webinar, which is how automotive and wind energy sectors are benefiting from the low cost of the carbon fiber. So the dilemma really is how to take the carbon fiber from supercars to just cars. So high volume, low cost manufacturing is what's required for automotive, let's say. And there is a dilemma when it comes to the cost. So you're looking at different areas in the production and where the reduction of the carbon fiber cost is one of the central, most necessary development that needs to be realized. But it also comes along with other improvements, which can be the high performance resins, which can be automated. So that's basically segueing into the next topic in the webinar, but how automation can actually reduce the cost as well. We also look at how cost-effective products can be produced and how production methods can be brought about with more efficiency and effectiveness. Combined with all of this is certainly the decisions that underpin the usage of carbon fiber, or for that matter, any material in the forthcoming era of composite development. And that would be the design and the ecological impact. And do we know enough and how to apply this in the real production scenario? High volume processing is another key indicator that the cost is really within the reach of not just the main manufacturers or the major manufacturers, but a wide spectrum of manufacturers. So if you look at the analysis on the right, you would see that as the price per kg or any unit you can take per unit is going down for carbon fibers, you see a concomitant increase in the consumption of the carbon fibers in the industry today. So that brings back some of the circular economy concepts that Salwan actually alluded to in the previous presentation as well. So how do we go from the very least or the least desirable methods of reusing something, which would be just incineration, landfilling, or energy recovery, and how can we avoid those pathways and just go to reusing, remanufacturing, and recycling of products when they reach their end of life stage? So that is where the circular economy comes into picture. So circular economy, more or less, is a closed loop recycling approach where you want to retain the materials for use and for circulation as well. And recycling in this circular economy context works best if the material itself is easy to transform. So you saw the natural fibers in the last presentation. So when I worked with natural fibers, and when they were actually in the composite, I guess, stage, you can't really change them or you can't recycle them to obtain pristine natural fibers. But that's not the case with carbon fibers, as you will see in the forthcoming slides. Circular economy, in general, looks at reducing the use of non-renewable energy. It aims at eliminating toxic chemicals and waste through better design of materials, products, and other business models as well. So in general, you look at two different types of circular economy. So one is an open loop, where you start with an original product or an original type of material. Then when it comes to the end of life, it emerges as another product. But if you look at a closed loop recycling, you're looking at something like, let's say, thermoplastic composite, where it's used, recycled, and reused, and that goes on for a certain amount of loops. So circularity usually is obtained by lowering the global cost. And when we can achieve a full loop, that would enable their application and incorporation into a wide range of fields and applications, because now we have reduced the overall cost. Because we are not remaking materials, we are not extracting raw materials again and again. So if you look at how we take the CFRP, or the carbon fiber reinforced plastics or composites, there are a number of steps to go to the recycled CFRP. So if you're looking at a closed loop or even an open loop. So there are several steps, and those would be the collection and segregation. They would involve removal of contaminants, shipping to a recycler, and then the recycling process. So the recycling, in fact, starts at the very end of this. So keeping that in mind, I would now like to focus on the recycling of carbon fibers and how it's done in the industry today. What are the different categories and methods that we look at for CFRP recycling? So CFRP recycling can be broadly categorized into mechanical methods, thermal methods, and chemical methods. So within mechanical methods, it's quite straightforward. You have a mechanical machine or an equipment which sizes down or grinds or mills the composites as received into smaller parts, and the fibers are recovered from the granulates. The thermal process applies some form of a heat and specialized equipment, and that could be under pyrolysis, fluidized bed processes, and combustion. Chemical, as the name suggests, would apply some form of a solvent, the combination of electricity and chemical, and also in some cases catalytic depolymerization. And there are several other branches of this as well. So if you look at the overall energy consumption, you have the mechanical recycling, which takes the least amount of energy. But you will also find down the line that mechanical recycling might not be the best choice or the solution for most of the recycling. Thermal recycling, on the other hand, takes a bit higher energy, and the chemical recycling takes the highest amount of energy. However, there are pros and cons of using a mechanical method, a thermal method, and a chemical method as well. So why are we so interested and invested in performing the recycling? The answer is quite simple, is because the carbon fiber composites, the fraction of carbon fiber composites and composites in general being used in aircraft today is increasing. So if you look at the latest statistics, you would say that up to 60% of, let's say, the Airbus 350 and its variants are using some form of carbon fiber composites. So which means that if we start today, the recycling processes, and we start to perfect these recycling process, they'll be ready by the time the aircraft that are being produced today reach their end of life, which is 20 years from now. So we should say that we are at the correct time period where we can start the major types of recycling and look at the pros and the cons and how each of them weighs against each other. So the first one is mechanical recycling. And as the name suggests, you would have some form of a comminution or an attrition or some form of a mechanical unit operation being applied to size down a composite as received or as sorted. So in general, you would see on the left-hand side, you go from a larger part or bits and pieces of composites all the way down to a smaller granulate. And on the right, you would see in general a granulator and how it works, and how we can also obtain different size profiles. So again, this is quite important because a different size profile of the recyclate is quite important for different type of applications. So if you're looking at thermoplastics and adding some, you would need particulates. If you're looking at geopolymers, you would need a different profile. And if you're looking again at thermosets, you're looking at almost continuous fibers. But in general, what you would see is that the fiber aspect ratio is quite short for the mechanical recyclate. However, a 50 to 65% of the tensile strength of the virgin fiber from where this composite was made is actually retained. So if you look at thermal processes and how they weigh against the mechanical process, the major difference being you're using heat. So the heat is from a temperature range of 450 degrees Celsius to 700 degrees Celsius, decomposing all of the resin matrices. So even the high performance thermoplastics or thermosets in that aspect would be completely decomposed at that stage, whereas the breakdown of carbon fiber has not yet begun. So that is the kind of, so to speak, a sweet spot where you would like to apply the thermal recycling methods. And within this, you can also do a combination of high voltage fragmentation and other type of processes as well. And you can, with a high amount of success, you can achieve very clean fibers from thermal recycling, because with the application of heat, the resin completely decomposes, and at that stage, you just have to wash off anything that is remaining on the fibers. Pyrolysis often is the most viable and sustainable processes in terms of the thermal recycling methods. However, it has its own cons as well, as we see in a minute. Chemical recycling is another method where you would almost always apply an acid base or another type of solvent. And as the name suggests as well, there is a wide variability in the terms of what chemicals you can use, at what temperature you can use, what equipment you're using, and for what duration you're applying this chemical onto this recyclable material, and what temperature are you using in this environment as well. So that brings upon a very large variability. So everybody almost always claims that their method is the best. So in this case, you use phosphoric acid and you obtain the degradation products and the liquid. So again, chemical recycling and these type of methods also produce in some cases. So thermal recycling in some cases produces the monomeric or oligomeric products, whereas chemical recycling also has the capability of producing degradation products, which almost you would say are not really useful in engineering sense. So in a chemical recycling method, you would look at disintegration of resin with acid bases and solvents, and you can have up to 97% of retention in the tensile strength versus the virgin carbon fibers. However, as with any size reduction method or recycling method, there is a loss of the original form of the fibers. And in this particular case, what you're looking at is the mean or the peak of the distribution of fiber length for the virgin fiber being higher than the recycled carbon fiber, which means that there is a degradation in the fiber length and thereby the fiber aspect ratio. So again, that would directly correlate to the fact that you are looking at a lower structural bearing capability when you are using the recycled carbon fibers. But in some cases, you can also see about a 97% retention in the tensile strength, which is pretty good. So one other angle is looking at what actually happens in terms of the value of the recovered fiber. So are we actually hitting a target? Are we actually able to produce fibers which are actually economically viable? So what you would see is different types of methods and how the unit cost per the unit mass of recovered fiber and the overall cost and where each of these costs go in the process as well. So with a variable recycling capacities, what you would see is some of the methods have a higher rate of producing recovered fiber and thereby the recovered cost. And thereby that really means that you can apply a recycling method and that is financially viable, even if you're, let's say, changing your business model to include, let's say, recycled fibers and you're trying to replace the pristine carbon fibers or the virgin carbon fibers as well. And as you can see on the right, the amount of recovered cost in terms of, or what cost goes into the waste, you would see that there is zero return almost for landfill and incineration, whereas there is a little bit of cost recovered in terms of the grinding, pyrolysis, and other types of recycling methods as well. So to summarize overall, what we witnessed today in the recycling space is that high voltage fragmentation, electrical fragmentation usually are particularly attractive. Rather than applying a single source of energy to break down the resin and other types of chemicals, it's usually advisable to apply high voltage and electricity. Within the thermal recycling methods, microwave is again revolutionizing the way we are looking at the recycling, because microwave reduces to a large extent the thermal recycling losses. Chemical recycling has its own cons, most of them being very high eco impact, and that's because you're using a vast amount of chemicals. But again, on the other side as well, you have lab scale applications of most of these chemical recycling, which really require significant effort to bring them to the commercial scale. And underpinning all of this is, again, to reiterate, the life cycle analysis are important to establish industry and customer confidence in recycling approaches. So on the right side, I have listed a few technologies on the top with the amount of retention of the tensile strength. So that gives you a good snapshot of what methods are usually more effective than others. So what you would see is the thermolysis or the pyrolysis type process and solvolysis, which use, again, heat plus a solvent, have a higher amount of recovery of the tensile strength versus the, with respect to the virgin carbon fibers. And we have reached such a stage these days where you have ELG and other types of providers, including Zoltec, which who are actually shipping out the recycled carbon fibers themselves as either in a woven, in a milled format, or any other format. So in terms of technology readiness, only solvolysis and pyrolysis usually are the desired ones. Whereas the rest of them require a large amount of rethinking or not economically viable or bear a lot of potential. So in terms of the applications and where we are taking the recovered carbon fiber, so you're looking at the number one stage is the alignment. The alignment becomes a large issue when you have to achieve some sort of a structural strength. So there are multiple methods where you can have proprietary methods, and there are certain routes that you can apply to obtain the fiber preforms, and you can combine them with polymers to obtain compression molded parts. There are methods where you can combine the recycled carbon fibers along with polymer fibers to produce preforms. and those can be taken into another secondary process such as a compression molding, and you can obtain semi-structural to structural parts based on that as well. In terms of non-woven applications, you can have them combined with these fibers combined with a number of resins, most particularly thermosets and thermoplastics as well. And in terms of actual automotive applications, now we are witnessing a number of these applications now being online. There are also advanced engineering applications where you can put them in smart textiles, not just as a smart textile itself, but also as a framework. So that gives a structural strength for applications where you require a little bit of additional structural strength as well. It's applied in 3D printing as well, and in geopolymers, combined with geopolymers. And in CFM, you have now a pultrusion line and a braiding machine as well, which I believe would be, again, providing some world-class applications into the use of recovered and recycled carbon fibers. So at the end, I just wanted to focus very quickly upon the challenges. So most of the challenges come from the low reproducibility of the recycled products. So what to do, what are the standards, how do we make these acceptable for the consumers and the industry? Do we have reliable and continuous supply of the recovered fibers? And one step backwards is do we have enough supply of the actual recyclable product? So if we don't do that, there is a diminishing market and all of this effort is effectively lost. So in terms of opportunities, fiber alignment to increase the mechanical performance is one of them. Using degradable thermosets and liquid molding compatible thermoplastics such as helium or nylon 6, they have a tremendous promise. You can replace thermosets with high performance thermoplastics, which wind turbines are actually going towards. Altering surface chemistry and involving nanomaterials within this to increase whatever is lost in terms of the retention of strength and other properties. Designing initially for structural applications rather than non-structural applications, and that will drive the production of high quality recovered fibers. And policy and legislation wise, just looking at the techno-economic and ecological impacts, and phasing out unviable methods such as incineration and landfill will also help. So with that, I hope I gave you a good introduction or insight into the area of carbon fiber recycling, and thank you very much for your attention.
Thank you, Venkata. And certainly, we said that the carbon fiber recycling is important. And also there's a driving force because it's high value materials. And then if we can successfully get that will be good. Any questions from audience? I particularly want to, Venkata, you probably can show in the Q&A or chat. We recently published a review paper in the Composite Part B, particularly on this carbon fiber recycling. And then we talked about the various of method, and then the currently who are the companies doing has a lot of involvement in the carbon fiber recycling. At this stage, like you compare with the economic viability, looks like the pyrolysis is the way, because a lot of companies are doing that. And then that's in terms of like the energies you input and the values you come out from the process, recycling process. So Venkata, you can provide that the link or just the papers, the pages or the journals. Okay, so now we have our presenter, and then Emmanuel. He is from France. So I really need to thank you, like the time difference. So it must be very early morning. This is also showing the center of our activities. We not just Australia, we also do collaborate with globally the other countries. And then he is going to give us the talk on these the composite manufacturing in the filament winding. So as I mentioned, like from the aerospace usage of the composite material, which is the autoclave is the main method to get the high performance, and then come to those non-automotives and then the other manufacturing processes involved. So I hand over to Emmanuel, and then the floor is all yours. Thank you.
Hello, you can hear me?
Yeah.
Yeah, okay. So I would like to introduce Mftec. So as you say, we are a French manufacturer of filament winding machine. So we are based in Normandy in France. And me, I am the CEO of the company Mftec. So Mftec, we have been established in 2004. So the name of Mftec is coming by a family name and my business partner, Arnaud Ménard. We are close to Paris, 2 hours of west of Paris. And since 2018, we belong to Coriolis Composite group with a supplier of fiber placement technologies. Number of collaborators, we are around 150 people, machine all over the world, supplied more than 190. We plan to be more than 200 this year. And with Coriolis and Mftec, we share around 50 patents families. The main activities for Mftec, this is the design and production of filament winding solution. We have also 2 research centers, one for filament winding in Normandy and one for AFP process in Brittany. The production of filament wound tubes composite also, this is a production that we have at Mftec, and we use around 4 or 5 tons of prepreg to produce some different tubes for different industries. Why we became a world leader, so I like to say that, maybe because we are alone in the world to use the robotics. The winding robotics open new horizon for the future. This is really easy to integrate, and we reduce the footprint of the machine. This is very interesting because the cost of the square meter is higher and higher everywhere in the industry. Plug and play, so we can use some different components from the industry and plug them with the robot. It's easy to install too and maintain all over the world, because we use some KUKA robot, only KUKA robot actually, and we have a lot of technical assistance all over the world from KUKA, and this is very interesting for us for training, to train our customer, but also for maintenance service on the robot. So we save a lot of time for that, and spare part for sure in case we need. And we discovered that robotics can create new degrees of freedom for the filament winding technology. We know well 6 axes for the filament winding robot today, but with the combination of 1, 2, 3 robots, or the movement of the robot itself, we can find some new solution. So the safety and the accuracy by Mftec, this is a question that we have often by our customer. What is the accuracy and of the robot itself? Because in the past, some people they were thinking that the robot can become crazy or something like this. But now a robot is really something very safe and accurate. We can tell that because we can also for the accuracy of the machine, this is accorded to the ISO 9283 standard, and also with the safety, we use some more and more the KUKA safe operation connected to the cement safety integrated. So it means that with these 2 blocks, we have a complete machine, really safe, and you cannot have some crash or accident with this. And this is the most safe machine compared also to CNC homemade CNC machine. The robot is clearly the most safe system. So we'll present a video. So this is Mftec today. Mftec, this is 3,400 square meter to build the machine, and this is one of our mechanical guy allowed to do these things. And we use SolidWorks to do our machine. So we have 4 or 5 office designer to design all the machines today. And we are involved in selling this application and all kinds of industries or sports. This is the inside again of Mftec. During the commissioning of several machines. And today we are 30 people inside the Mftec, and with engineers, PLC programmer, robotician programmer. So we have all the team. So here we have example of a new movement on the machine. So this is the inside of the Mftec production site. We have two filament winding robots where we produce some kayak shafts, some tubes for different applications. Here, the beginning of commissioning of an installation for Airbus. It was for the air inlet for acoustic panel on the engine. So this is myself. So the project management, we have a team of project manager, and we are able to manage also with Coriolis now. We are able to manage the project from different customers all over the world and to do all jobs for you. So the research and development, it's a big part at Mftec. We do a lot of research. So we have a new lab where we can use different technologies, so pre-preg, wet winding. We have also M3 from RAU system where we can weld some thermoplastic. It's an old example of our technology for the fiber placement. And here mechanical stuff that we can produce. So the parts of the bike we did. So now I would like to introduce the different process of Mftec. So at Mftec, we have 4 processes today. We are running all over the world. And one is for the future, what we call the MF5. So the first one is the MF1. So this is the classic winding machine, maybe you know that. And with Fibre carriage on the robot, we don't have limit size. So a small video just to explain. So we have a spindle frame where we rotate the mandrel and we cover with the fiber by the movement of the robot. So it can be made with pre-preg, with wet winding, all kinds of solution, with electronical tensioning system, mechanical tensioning system. So it's one of our application today at MF. So the MF2 process, this is new winding system on the robot head for cantilevered and small mandrel, elbow, complex parts. It could be some small gas tanks also. So another video to show you. So we have a static eyelet on the machine to deliver the fiber on the tanks, and the wet system, also the drum resin bath is static. And we move the parts on the front of the eyelet with the robot. And we included the spindle system into the robot itself. So it's a very good process. This system now it's for oxygen bottles, but we have also some example for LPG system, some gas bottles, or for some other in Belgium, for example, for beer kegs. The third one is the MF3, the most innovative method today by moving the mandrel in 3D and the highest winding precision that we know today. And on this system, we can have high degrees of automation. So it means that this is our R&D machine system. So this system we sold all over the world to produce H2 tanks. For hydrogen, for a passenger car, for trucks, for boats, and all the system. And with that, we can imagine that this gripper is fully automated to take the parts and to load from the cart and wind and auto-attach and cutting the fiber. So we have all degrees of automation on this machine. Now I would like to go on the MF4. So we developed this system, the MF4. Also with a robot, so we move the mandrel because on some specific case, by the use of pitch fiber, for example, compared to pan fiber, we cannot have a sharp angle on the system. So we move completely the manual to avoid fiber twisting. Also, with this system, we can build some huge tanks. And with this system, we avoid to have a big carriage with the resin bar, the krill embedded together, and we are moving. So it's more easy to move the manual and not to move all the system. Also, we can imagine to have a lot of automation on the system, to have different kinds of head. And one head is for glass fiber, for example. The second head could be for carbon fiber and different. And we can split with automated system and grippers to load the tool that we need and the fiber that we need. And now we are working on the MF5. So recently, due to the COVID crisis in France, the governments help all companies. And we are working on new kinds of machine that I will introduce later. So the Mftec today is working on a niche market. Year by year, we develop our activities on different kinds of industries, so from aeronautic to sports. And we have all kinds of machines, and we develop all the time. We don't have a standard machine. We develop all time for our customer, our machine. So it's not standard. All times we make some tuning or fine tunings on our equipment to assist our customer to produce the parts they want to do. Turnkey project. So we work several times with some others company, and now with Colliers Group, our mother house, that we are a bigger group. So we can install some complete turnkey plant. So here we have an example at Airbus in France for the air inlet system. It was for the Airbus 380, 330, 350, and for sure the 320 Neo. So we build in partnerships with a bigger group in France, with Actemium. It's a part of Vinci Group. We build this factory all together, and we were involved completely in the project. So the future by Mftec. So from 2000 to 2021, we supply more than 95 equipment, supply all over the world. We adapt all time on the market demand. So we can have some thermoplastic application, welding robot, ultrasonic cutter, plasma treatment. All these components we can plug on the robot. So it's like a kind of Lego system for us. And what we see today, we need more and more automation for sure, but traceability is very important because our customer, especially for the production of H2 tanks, they want to know who produced the part, which kind of machine, the batch fiber, batch of resin, all these things we need to give to traceability to our customer. So we can export all the data on the server of the customer, or the customer can come into our machine to take all information where it's needed. So it's a very important process today for this automotive and H2 production. The H2 market now this is really the new target of Mftec. If we compare in the last days or today, the classic filament winding technology is really poor by low automation, wet winding, cleaning, time to change the spools on the krill. Today you have to know that just to change the spools on the machine, to produce some H2 tanks, some other parts, it's nearly 20% of the life of the machine. So this is not acceptable for the automotive production today. So the solution for tomorrow by Mftec, we have to go for filament winding techno to 4.0, full robotized units, full automation. The pre-preg for sure is it's a key in the process, and the fast winding. So we have to increase the speed of the winding on the wear machine. It's why we produce this new MF5. So just to estimate the growth of carbon fiber by tonnage for hydrogen in the world. So the estimation for today, it's quite slow, it's okay. But in 25, sorry, we will need 10,000 tons of carbon fiber only for the H2 market. And 2030, it will be around 60,000 tons of carbon fiber. So for sure, this market of H2 will boost the filament winding market. So it's why we develop our new machine, and we receive massive investment and financial and human from our mother house to develop this new roadmap of Mftec. So we start in 2004 with a small robotic system with the MF1. 2021, we start the MF5. 22, this machine will be fully automated. We will increase the sales, and our goal is to become the world leader for filament winding machine on the H2 market tomorrow. So this is the growth of the H2 market. Compare today to the automotive with petrol. So it will change in the next year, and the European Union explained in the last days that they want to increase totally the number of hydrogen cars and to reduce hydrogen and electrical cars, and to reduce totally the number of cars with petrol. It will be prohibited, I think, in 2035 to sell some cars with petrol. So to wind all the product of our customer, we decided this year to produce our own filament winding software. This is a unique software today. Mftec is the only solution where you can see your machine and the product you want to wind on the machine. So we save a lot of time with this new software, because the classic software known in the world today, you just see the parts that you want to wind, but you don't see your machine. So you have to start first to wind on your software, and after you have to go on the machine and to load the program on the machine and to check what's happened. So with this new software, you can see all the things that you need on the machine, and you can make some drawings, and you can make a lot of things. The official launch of the software will be in September 21, so it's tomorrow. And now we are applying some new options that we can control the tension of the fiber with the software. We can control the air inside the liner of the software, the resin temperature, and all these things will be managed directly by the software. So this software is the experience of our last 20 years in filament winding technologies. So we want to have all options. So this is something new in the world of filament winding. So where we are located, all over the world with Coriolis and Mftec, we share some agent all over the world, and some technical crew, and some reseller. So it's where we are located. So you can see that Australia, we have no one at the moment, but I will be pleased to have a new agent in Australia. The market is starting to be bigger and bigger, and so you are welcome to make your proposal for that. So a portfolio of some our customers, so Mftec and Coriolis, we work a lot with different partners all over the world, and in different technologies, but we are close also with Coriolis to aerospace or military application, because we have a lot of projects for military, but also aerospace, and so it's nearly the same customer, but not for the same product. So thank you very much for your attention, and if you have any question, you're welcome.
Thank you very much, Emmanuel. Certainly, I can see the company and your products is in the right area, like with the hydrogen economy and then the hydrogen pressure tanks. There are going to be lots of opportunities. There's lots of demand from the hydrogen pressure tanks.
So the demand for tomorrow is huge. The number, when we discuss about I saw the previous presentation about the recycling of the carbon fiber, and also that some people they plan that the price of the carbon fiber will go down, but I'm not totally sure about that, because more and more the industry of automotive will need some carbon fiber. And I think it will be very, very, the demand will be so huge that I don't see that a price reduction for that today. I'm not sure, but it's, yes, the demand is incredible today for the carbon fiber, and especially for H2 tanks.
Yeah, and also like all those your pressure tanks, the filament tanks, the recycling is an issue. A good point is all those filament tanks, you have less of the contaminations, because all the material pretty much is the carbon fiber and the resins. So it's the good the products to choose for the recycling.
Yeah. But today, what we know for the recycling, it's a bit complex because we use most of the time automotive. They want to have the cheapest price as possible, so they go to thermoset because thermoplastic is too expensive. Or if we want find a way with carbon fiber with not too expensive, the machine will be expensive because we need some laser, we need a high degree of safety, and so the route and what to choose today is only for automotive is thermoset, and with the lowest cost as possible. It's why they want to increase the speed. If the Mftec is developing a very fast machine, the goal today for Mftec is 6 meters per second, the speed of winding, and the speed today is 1 to 3 meters per second of winding. And the goal is to save time on the production on the machine, because they know well that the price of fiber cannot be adjusted. Resin, it's the same. It's quite difficult to know.
Good. And I think the USQ is already start to talking, and then because we are also going to set up the filament winding here, and then it's the very the area which is full of the opportunities, and then there's a lot of interesting things you can do. Thank you very much, Emmanuel.
Yeah. Thank you, and hope to see you soon in Australia or in France. If you have any question, you can contact us on from our website, mftec.fr, or on LinkedIn. I am on LinkedIn, so you can join me on LinkedIn.
Thank you very much. So, like, it's early morning there, and I appreciate your effort. And then thanks.
It's 9 in the morning, and I'm actually in the north of Europe. I am in Oslo. I don't know. Okay. It's very. I travel all over the world, but hello and goodbye from Oslo. Thank you very much.
Thank you. Okay. As I said, we also have a journal called Composite Part B. USQ, myself involved as the editor-in-chief. So I use this opportunity talking about the journal, because once you run the highest impact factor journals, and then we have the responsibility to look at what is going to be the research activity or research directions in the composite area. And then we also try to use this kind of define the directions and then apply to our research activities. So you probably from my next few minutes talk, and then you say why we're doing those research. Okay. So in the composite area, we have mainly these 4 journals. We have the Composite Part B, and then we have the Composite Science and Technology, and then we have the Composite Part A. And then just last 2 years, there's a new journal, it's a Composite Communication. This is for the short papers. I put this impact factor. We just recently, 2 weeks ago, we got this new impact factor. So we are the 9.078. And the size score. So also like we are the 14.5. So you see the other journals. So impact factor, we are the 9+, and then Composite Science and Technology is 8+, and then Composite Part A is 7, and then the other one is 6. So Composite Part B really is the highest, we say impact factor, the #1 impact factor, size score, and then publication numbers. So all those 3 parameters were in the #1. Probably later are going to introduce what's the difference in impact factor and the size score. So that is the good news we received 2 weeks ago, and then from the Web of Science. So impact factor is the parameter developed by the Web of Science, and then they use the citations of the last year's citation of year 2018 and year 2019's papers, and then divide by the number of the papers. So you got this the numbers, and then here this one I put over 4 journals, and also see the growth, the development of the impact factor. So you can see like composite part B now is in the 3rd year. We are ranked as the #1. So certainly, like strongly, we say in the #1, and then the #2, the composite science technology is 8.5, and then the other one is a 7 point something. So we are very pleased with that result. And then the size score, that's another system. So it's a Scoopers. Scoopers develop their parameters to evaluate the quality or the impact of the journal. And then you see the composite part B, so that we are the 14.5, so it's much higher than the other 2. The difference with the size score is they use the 3 years publications, and then the citations. So you can see the all citations in the last 3 years, we have 52,000, and then it's divided by the number of the papers. And you can, the size score, we have the highest, and then the number of papers, we also higher than the #2 and the #3 combined. So the size score is looking at the quality of the journal, so the papers published, the qualities, and then the number of papers, it means the influence of the journal in these communities. The journal, we have the 3 strategies, and then that's, I think we have the right strategy. That's the reason we have a good achievement. So the strategy, we said, it's a faster, better, focused. And then the faster, we try to process the paper as quick as possible. And then that is means the result, your research result can quickly be processed, and then if it's acceptable, then published in the journal, and then you can disseminate it into the communities. So we have the aim like 2 weeks of the initial decision, and then 1 month we can have the final decision. The best, we certainly will want to publish the best paper, and then put the journal in the high standard. Currently, we have a rejection rate more than 80%. And the focused, we have a clear the area, like the definitions, where is the areas we want to publish the papers. So these 15 selected topics are going to mention in the next slides. We have also other things like to promote the visibilities. The paper published in the Composite Part B, you can you can get the best visibilities. So we have those social media from the website, and then also we have the WeChat, the linking to promote your papers. And then we have a good relationships to the other journals. One side is because 80% of the paper are going to be rejected from Part B. And then those papers, some can be transferred to the second tier of the journals. On the other hand, it's also, we have a good relationship with the other journals. So you have papers submitted to the Science, Nature Material, Advanced Materials. If not being accepted by there, you can, like we provide you as the candidate of the choice, like submit to us. So currently, we're already in the #1 journal in the composite area, and then 9.1. So we are expecting we're going to go to impact factor 10 very soon. The journal is like to promote those kind of partnership. So it's the journal, and then our author and the reader, and also the universities. So we actually working together to help the research area, and also help the community. And then I will mention that again, like we also try to make the connections of the research and the industry, so promote the industry as well. So the journal is very much focused on engineering and applications. If you look at our cover, you can see like you have the aerospace, the airplane. You can see the automotive car. You can see the wind turbine blade. So those are the areas of composite material currently being used. One area we still publish the traditional fiber composite, and then it means like the fiber reinforced, the glass fiber, carbon fiber reinforced, the polymer-based composite. And then as I mentioned previously, we see this trend. The material, composite material, has been in the aerospace, and then played a very significant role there. You also can see even the aerospace, there's growth in using of the carbon fiber composite. So those are the high end of the usage. But we also see another even more significant development is those carbon fiber composite, and now it's moving to much more large volume and the low cost applications. So that is in the automotive, wind turbine blade, and then Emmanuel was talking about the compression gas tank, so use the filament winding, and also in the infrastructure, and then marine applications. We also do the traditional like composite design, characterization, performance, failure analysis. So that is the composite material we use to evaluate the materials. Venkata was and also Salwan was mentioning the recyclability, sustainability is a big issue, and then particularly if we are going to increase the volume of the composite materials. We also have the other area is the functional material. So that is related to Pingan's frame retardant and the fire retardants. And then the composite in the electronic, magnetic, optical, all those areas, the new applications. We have this nano composite. So the composite using the energy, catalyst, those area, and then carbon related, these new development in the composite. And then the last one is the bio-based composite. So the bio-based, there's a natural derived material. So you from the plant, from the animals, from this the microbial fermentations, all those. And then we also learn the material from the nature. So those bio-inspired, biomimic materials. And then the last one is the materials using in the bodies. So biomedical applications. That's the new, certainly like it's become more and more important because some of the body implant materials, the composite material, there's a particular role we can play. So when you submit the paper, so the process is there. So when you paper being submitted, and then the editor going to do the first decisions. So we said we have a high rejection rate. So 60% going to be rejected as the first decision. So that's called desk rejections. And then 40% of papers, we going to assign the reviewer. And then the reviewer send the report. And then we look at the report again. And then there's a 60% being rejected again. So only those 40% of the 40%. So about 16% of the papers, we will ask you to revise to, so you have going to do the major revisions. And then after the revision, and then probably there's some further rejections. So if you ask like the editors and how they can select the criteria, they select the papers. The key criteria is this three, like the novelty. Do you develop some new things? And then the quality of the research. And also the alignment with the journal's scope. So these 15 defined the topics. And then the additional consideration, certainly like the presentation, the quality of the figures, tables, photos, and then the quality of the technical narratives. And then we also do the similarity and the duplication submission check. So when you submit the paper, there's certainly like you need to pass lots of checkup. And then you see all those editors and reviewers to try to queue your papers. So certainly it's the hard journey. But eventually your paper has been accepted, then it's congratulations. And then we're going to send that message. So as the author of the JCOMB, and then you are now the co-member of the communities. Last word I want to say, like we running this #1 journal in the Composite, and then we kind of feel like we have this responsibility. And then mainly these three. The first one is we are together with the author and also the research communities to define and promote the future direction of the composite research. In this one, give you some examples, like the year before, we running a special issue which Pingan was guest edited particularly in the flame retardant area. And then last year we did one is the composite recycling special issue, and then the other one is the thermoplastic composite special issue. And then this year, we are developing another special issue because it's now this year or next year is the 50 years of anniversary the carbon fiber composite. So the community are getting together to think what's the future of the composite materials, and then what's the implications there. So we're going to invite the leaders in the research areas to ask their view, and then those the predictions are going to play an important role to our young researchers and also the researchers, the whole academic and the industries. So that is the first we see our responsibility. And then we also, with this research, define the research area, and then the center is also, we can see, even from today's webinar, you can see why we selected those areas for our activity, research activities. And then second is we always think like the research need to be driven by the industry. And then, so it's also our job to promote the linkage between the research and the industry and help to do the technology transfer. And then the third actually is also the most important one is we sort of have this in our shoulders. We need to attract the young talents to our composite area. And then always, because the manpower, the people is going to eventually drive the research and drive the technologies. So develop the task force and then promoting, helping them in the career development. So the journal also can play the role. So thank you. So any questions about any questions about these journals? Happy to answer. And also, like, if you have any visit the website of the journal, and then if you have any questions, you can send me an email, and happy to talk to you. And then certainly welcome if you have the good work submitted to us. Thank you very much. Okay, I think I already over the time. So today I want to thank all our speakers. Some is from the overseas, and thanks for their contributions. And also I thank you very much, our audience. Your participant is important, and your question, the interaction is also very important. I thank you, Shusen, the center's CFM, which put together this the webinar, and thank you very much for organizing that. Thank you. And then with the center is going to have a more webinars coming, and then hope you can make aware like the next things coming, and then if there's opportunity, you can also visit us. We hope the situation, the COVID situation, can be finished soon, and then we can have these face-to-face workshops. Thank you. Bye-bye.